So for our number one, we have this chemical structure here. I mean, the structure that we have here is the as in an alkene. All right. So we are tasked to name this structure, and the first step that we're going to do to name this alkene is to count how many carbons there is in the parent chain. So we have 1, 2, 3, and 4. So meaning we have 4 carbons here. This means that this alkene is a butene. Alright, so I'm going to list here as a butene. This is a butene. And we're going to check if there is a substituent, which there is, and it is located in um, the third carbon, which will serve as our prefix. So 3, and this has 1 carbon only, so this is a methyl. So I'm going to do it first. Okay, sorry for the delay. So we will begin constructing. This is 3 because this prefix or the substituent is located in the third carbon. So 3 hyphen methyl because this is only 1 carbon. 3 methyl, and then we have our double bond here, which is located in the first carbon. So this is going to be a 1 hyphen, this is methyl hyphen 1, and then we're going to have hyphen again, butene. So this is called 3 hyphen methyl 1 butene. This is how we got our answer in our second problem. We have our alkyne here. The structure of our alkyne is having that it is composed of 6 carbons in the longest parent chain. So to clarify, we have 1, 2, 3, 4, 5, 6. So we're going to name this as a hexyne. Hexyne because of the triple bond. Now we have 3 hyphen methyl here because the third carbon is attached with a methyl. So automatically this is going to have a 3 hyphen methyl, and then our first carbon has a triple bond, so automatically we are going to have a 1 INE here. So to assemble this, or to sum this up, we are going to put the 3 first, or the methyl or the prefix before the parent chain. So this is 3 hyphen methyl and then hex hyphen 1 because of the carbon who has a triple bond present, and the YNE. So for our third problem, we have a cyclopentene here. Okay, so why do we call this a cyclo? Because this is a shape of a cyclo. This is attached to each other. Okay, so to name this, we're going to first have this. So the closest one is going to be here. So this is going to, we're going to start here. So 1, 2, and 3. Okay, so 1. So as we can see here, the third carbon chain or the parenting chain has an attachment with a methyl. So this is going to be 3 hyphen methyl. It's too big, and methyl. And then given this the form of this is going to be a cyclo. And then we have a 5 parent chain here, so this is going to be a pentene. And then the carbon, the double bond is in. So this is named as a 3-methyl 3 hyphen methyl cyclopent 1 in. Okay, so for our fourth um, problem, we are tasked to give or to draw the structure of the presented compound, which is the 1,3 hyphen hexadene. So yeah, I'm going to draw this one. We're going to point out some keywords here. Hexa means that this is 6 carbons, and dene, which means there are 2 double bonds. There are 2 double bonds, and the double bonds are located in this carbon, now carbon 1 and then carbon 3. So we're going to draw this like this. We have our first carbon, or should be 2, and then we have our double bond here, and then our second double bond, our second carbon, and then our third. And now the third one is having also our second double bond, and then H2, this is 2 guys, and then CH3. Okay, so let's check if this is correct. We have 1, 2, 3, 4, 5, 6, meaning this is a hexa. And then the dene, which we have our two two double bonds here in the carbon one, and then our carbon 3. So 1, 2, 3. So this is the third carbon, and it has a double bond. So we're going to read this as the structure as 1, 3 hyphen hexadene. So for B, we are presented with this name. So we're going to draw the structure of uh, this alkene. Yes, this is an alkene. So the keywords that we're going to put here is that we have 1 ethyl, and then we have 2 hyphen methyl, and hexene. So hexene means that we have 6 carbons in our parent chain, and we have 2 substituents here, dimethyl and dimethyl. Alright, so we're going to put our or draw our first carbon, which is having which is housed by a ethyl. So this is CH3, and then CH2, and then CH3, and then in our second carbon we have a methyl here. Yes, and one, two. We got 1, 2, 3, 4, 5, and then we have 6. Alright, let's check our structure. So in the first carbon we have our ethyl, so this is satisfied, and then the second one we have our methyl, so this one is satisfied also, and then we have our our double bond here, so this one is satisfied. So 1 hyphen ethyl hyphen 2 hyphen methyl hexene. For lesson 6 is that we're going to distinguish between cis and trans isomers. Okay, so cis isomers are the groups attached on the same side of the double bond. They represent similar page groups placed on the same side of the double bond. Okay, this is what it means. Suppose that we have an ethane here. Okay, and then we have a hydrogen here, and then we are going to put uh, no, going to put bromine here. Now you can say that this is a cis isomer since the two bromines are on the same page. What this means is that the two bromine is on the same side and the hydrogen is on the same side, meaning that they are, they're aligned. One example of so this is the example of cis isomer. Cis isomer, and we cannot call it a cis isomer if for once we're going to put a, let's say for example that our bromine and our bromine is on in the same bond. This is not going to be an example of cis isomers. Yes, they are on the same side, but they cannot be. I mean, this is not what it meant by the same side. It means that they are on the the opposite side of the bond. I mean, each bond should possess a carbon. I mean, the bromine that is on the upper part, so they're the same. So the bromine in the carbon 1 is in the upper side, and the bromine in the carbon is in the upper side also. So this means that they are on the same side, which means that the our isomer is a cis isomer, and this is not a cis isomer. So another example, let's say for example that our ethane has an HO and our bromine is transported in the lower part. So are they going to be called a cis isomer still? The answer is yes, because they're still in the same side. Even if the bromine is not on the upper side like this, they're still be called a cis isomer since bromine in the carbon 1 and bromine in the carbon 2 is on the same side. They are on the lower part of both carbons. So yeah, that is an example of a cis isomer. However, in the trans isomer, the trans isomers are on the other hand have features where similar side groups are located on the opposite side of the group. So this is the opposite of a cis isomer. Suppose that we have our Cl here and our Cl here. Okay, now our definition of cis isomer, trans isomer, is that the same side groups are on the opposite side. So Cl is on the opposite side, our chlorine is on the opposite side, so which means that our carbon 1 chlorine is on the lower part and the chlorine in our carbon 2 is located on the upper in the upper side. So this means that this is a trans isomer. This is a trans isomer. So for example, we have our Cl here, and then we have our H. Let's put H and our H here, and then we have Br here. So this is not going to be called a trans isomer since the opposite side of the group has isn't identical. Alright, this is a chlorine and this is a bromine. So this is wrong, and this is the right one. So we're down to our second question, which is we need to explain the requirement for cis and trans isomerism of or for the alkenes. These alkenes lacking an L. Okay, this is how we do it. To be able to identify a cis or trans isomerism in an alkene, we need to observe two identical groups on either end of the double bond. If the alkene only has an identical group but atom substitute on both ends of the bond, then it would not be possible to have a cis trans isomerism. So this is I'm going to provide you with an example. So as discussed earlier, we have a Br here or bromine, and we are going to have our hydrogen here. Hydrogen groups. So this is a this is an uh, I mean this bond is possible to have a cis and trans isomerism because they pass the requirement for this to be um what do you call this? Okay, so since bromine is in the upper part and the bromine is also in the other part, this is a cis or trans isomerism and it is possible. So what is the name of this? So this is going to be a cis alkene. It's a cis alkene, and yes, this is okay to have a cis or trans isomerism and it is possible. Also, we have H and we have Cl here. So we have H, and in the other hand we have our Cl here. As you can see, both chlorine and both chlorine are on the other side, is in the opposite side of the bond. So chlorine in the first bond is in the upper part and the chlorine in the second bond is in the lower part. So this means that this is a trans isomer, trans alkene. Okay, this is an alkene. Yep. Okay, so in this side, this is possible. This one is the possible side. Now, the not possible. So NP means not possible is that, for example, we have our PR here bonded to our carbon, and then as you can see here, we have only bromine in our first carbon, and the second carbon does not have a bromine, a similar compound. So we have a hydrogen here and a hydrogen here. This means that bromine is the only one carbon and it is not possible to have a cis or trans isomerism in this structure. Another example, oops, press and going to draw H and H and H. So as you can see here, it is still an ethene. Okay, this is an ethene. So is ethene eligible to have a cis or trans isomerism? Of course no. And the same as this. Okay. So for our third problem, we are trying to give three examples of a cis isomer alkene, and then we are going to demonstrate how they are named. So in my screen, I provided you guys a three different types of um, cis isomer. Okay, so in the first one, we have our classic CC. The carbon 1 in our carbon 2 is on the same side with the carbon 4. So this means that this is a butene because this is a cis. So this is a butene because carbon 1 should be included with our in our parent genes as stated in the rule. So this means that this is our starting number or starting carbon or top carbon is going to be here. This means that our carbon which is linked to the double bond will be going to be 2, and then the following carbon is going to be 3, and the carbon in the last part is going to be the fourth one. So this means that this is going to be a butene. So cis and butene because the double bond is placed on the second carbon. Okay, so I'm going to delete this one. So in this second example, we have an ethene here, which are respectively bonded with their own chlorine. So the chlorine is on the same side. They are on the same side. This means that this is a cis, and we have our hyphen here. So cis hyphen dichloro because this uh dichloro because they are two chlorine. So we're going to put this as our prefix. So this is going to be cis hyphen dichloroethene. Ethene because we have uh, only two carbons and a double bond. Okay, for our last part, we did that. Okay, so again, we are on the same side. This means that this is a cis. Bromo because they have the two. We have two bromines. This means that this is a dibromo, and then ethene because we have two carbons bonding with each other with a double bond. So again, this is a cis dibromoethene. So we are down to our number 4, which we are going to give an example of a trans isomer of key. So this is the same. We're going to give at least uh, no, three examples of a trans key. So again, we're going to okay. So as we can as am I recording? Yes, I'm recording. Okay. So in our carbon is on the opposite side of the bond. So this means that this is a trans isomer. So again, in the rule, uh, we're going to include carbons as our parenting chain, and then 3, and then 4. So This is a transbutene, and the another example. So we have our CN and then H. So as you can see, our chlorine is on the opposite side of the bonds with of course respect with each other. So this means that this is a trans. Again, it's a trans isomer, and based on our structure, there are two chlorines. So this means that we're going to have a dichloroethane. Dichloroethene. So again, this is a trans. Oops, this is an A. Trans hyphen dichloroethene. And in our last um, example, we have our bromine, and then we have H. So this is pretty much it. So again, I'm going to repeat what we learned. So bromine and bromine in the bond is not in the same side, which means this is a trans isomer. A trans isomer, and then since this is the two there are two bromines, a dibrom. We have dibromo as our prefix, and then 18. In our lesson 7 learning activity, which is this one. So in number 1, we are tasked to assign or which member in each of the following sets ranks higher. So basically, we're going to rank these two sets as of which of them are more higher. Okay, so to rank or in order to rank these kinds of chemicals, we need to rank them based on their atomic number. So say for example that chlorine and oxygen is chlorine is much more higher, or chlorine ranks the highest more than oxygen and nitrogen. Okay, so we're going to base the rankings, or we can determine if the element is more higher than the other one based on the atomic element. Okay. So here we have hydrogen is compared to bromine. So as we can see in our chart here, hydrogen has an atomic number of 2, while the bromine has the atomic number of 35. So in this case, 35 ranks higher than 2, which means that bromine ranks higher than hydrogen, which is only has a 2 atomic number. This means that bromine ranks higher. In B, we have fluorine versus bromine. So bromine has 35 again and 17 for fluorine. This means that bromine ranks higher again. Now, in CH3 or CH2 or CH2 bonded to CH3. Okay, so in this case, CH3 is much more smaller compared to CH2 to CH3. So again, CH3 ranks CH2, CH3 is much more higher than CH3. Okay, we have D, which is NH2 versus OH. So if we look in our ranking, we have N here, and we have our OH here. This means that OH ranks higher, which means O ranks higher than N. So this means that OH ranks higher than its opposing element. In E, we have CH2OH or N versus CH3. So obviously, CH2OH ranks higher than CH3 because CH2 has oxygen, which means that oxygen has the atomic number of 8 and C or carbon only has the atomic number of 6. In F, we have CH2OH versus CH double bond with O. Okay, so you might be saying that CH2OH is much higher than CH double bond with O. But we need to remember that double bond means that the one that is bonded is being doubled. So even if this is just a structure, we can see that this is a CH and bonded with a double oxygen. So with these two oxygens combined, CH double bond O ranks much more higher than CH2OH. So again, A is the answer of A is Br, and B, the answer of B is Br. In C, the answer of C is CH2CH3, and D, our answer is OH. In E, our answer is CH2OH, and in F, we have CH double bonded with oxygen. Our task in number 2 is to assign E or Z stereochemistry to the following compounds. We're going to assign if this, we're going to decide if this compounds presented is Z or E stereotype. So in E, E means that the bond is the compound is what should we say, E is equivalent to trans. I'm going to delete this. E is equivalent to trans, while Z is equivalent to cis. So basically, for our A, we have C double bond with another C, C and then CH2, and then OH, and then we have Cl, and we have CH, CH. By the way, guys, this is G. I just wrote it like 5 G, and I'm sorry because I'm terrible at writing with PC. I'm not used to it. So basically, this is the compound that we are provided. So this is the structure. All right. So how do we decide if this is a Z or an E compound? So similar to as of how we know that if the structure is a trans or cis, we do this. So instead of the compound is in the similar side, or the same compound is in the similar side, we decide, or we get the basis of the low or high level or rank, instead of basing with the compound that we have in the cis and trans isomerism. So what I meant to say is that if we compare CH2OH to Cl, then of course Cl is much more higher, and CH2OH is much more smaller, because O is 8 and Cl is Cl is 17, and here we know that CH3 and CH, it has 2 here, CH2 is much more higher than H3C or CH3, because with hydrogens of C, the double carbons combined their numbers, they produce a bigger rank than a carbon which has only one. So so H, and then this is L. So as of what I've said earlier, we base our findings on the outcome. So instead of the elements, we use, or we base our judgment on the high, or the placement of the high and the lower rankings. So based in our diagram, in the screen right now, the low ranks is on the same side, and the high ranks is also on the same side. So as I said earlier, this is a E compound. E compound. Oh no. So as I said earlier, this is a Z compound, because Z is equivalent to a cis isomer, and E is equivalent to a trans isomer. So this is a Z compound. So the answer of our first problem is Z. Okay, next we are presented with our problem letter B, which has the structure of C double bond with another C, and then It is, so the second bond has a C2CH. So we have an ethyl here, and then we have uh, Cl, and then it is bonded with a 3HC. So this is 3. And then we have CH2CH2, and then we have CH3. Okay, so if we analyze this, Cl is much more higher than O, because Cl is rank 17 and O is rank 8 only. So okay, here's my mouse. So this is an H and this is an L, and then we have our CH2, CH2, CH3. So based on our analysis, CH2, CH2, CH3, or the lower part of the bond in the second carbon, has a much more count, has a higher count of carbon than the upper one. So this is only carbon, so ethyl, well this is a propyl. So this means that this here, this our propyl here has much more rank, has higher rank than our ethyl. So this is an example of an E stereotype kind of composition. So why E? Because H is not parallel with H is not on the same side with the H on the other side. So H, our Cl, is in the upper part, while the the higher rank in the other side of the carbon is on the lower part of the bond. So H is on the same level with L, and L is on the same level with H. So this is like a trans isomer. So this is an E. Okay, so on to our letter C. We have our letter C here. For our C, we have okay. So this is a C. So this is what the structure in C looks like. CH2, and we have an NH2 bonded with one another. So let's cut the chase. Let's determine or analyze the right side first. So CH is more lower than the H because there is a nitrogen present, and nitrogen is much more higher than carbon, which is only 6, and nitrogen is has a atomic number of 7, which makes the CH2 and H2 ranks higher than the CH in the upper one, or the upper bond. So in our left side, we are provided with an H in the upper level, and in the lower level we are provided with a CH3C. So let's analyze and place the order of this or the ranks. So um, the lower bond, the lower, the lower here is has an has a carbon. So we know that carbon is much more higher than hydrogen because carbon is 6 and hydrogen is all 2. So which means that H3C is much more higher than the part in the lower here and hydrogen. So based on our findings here, the lower ranks is on the same side, and it is also the same on the higher ranks. So this is a Z stereochemistry type of compound because H and L and L is on the same level, which is the same with the higher ranks too. We're down to our number 3, which we are tasked to describe the 4 kinds of organic reactions, and we have to give one example each. So for our first kind of reaction, we are going to be demonstrating the addition reaction. Addition reaction. Okay, so basically, addition reaction happens when two reactants get mixed and interact with each other to form a single new product. In this reaction, no atom is left unpaired. Okay, so for our example, we have CH, or we have an 18 which is bonded with 2 atoms. And 2 atoms with respect to each other. So if we are to add Br, double bond Br here, the bromos. So addition reaction happens with acid catalysts like heat. So yeah, heat, and then so the result of this is that C is no longer be it will be no longer have a double bond because Br, or the 2 bromines, is on being added on the structure. So this means that there is no atom left behind. So double bond. So this is going to be a dibromoethane. It's going to be a dibromoethane. So the second reaction we are going to describe is the elimination reaction. So basically, this means that in this reaction, single reactant becomes 2 products. This means that atoms and or groups of atoms are removed from adjacent carbon atoms. So we have an example here. I'm going to present you with an example. So suppose that we have an ethane here. So there's no double bond, there's no triple bond, just a regular ethane with a complete 3 atoms, hydrogens, I mean. So in order for an elimination reaction to happen, we had to have or to expose this with a a acid. So, say for example, we have an acid catalyst reacting with our ethane. So this is an acid. It's going to have an it, it is going to remove the lower parts of both of their hydrogens. So without their hydrogens, these two hydrogens, the, they are forced to have a double bond. So this is going to be this is going to be named as an ethene with a double bond. So H. So this is an example of the elimination reaction. Okay, so now we are down to our last lesson, or lesson 8. And in our first problem, we are tasked to simulate the finished product of these two compounds. So what we have here is a cyclohexene, as cyclo because this is shaped like a ring, and it has 6 sides in total, and it has a double bond, so this is the cyclohexene. And this is a chlorine bonded with hydrogen. So this is a hydrochloride compound, and yeah. So if these two will be mixed, the final product will look like this. Okay, so why does this happen? Because based on the Micron-Combs rule, the hydrogen is attracted to areas which has fewer hydrogens, which has fewer bonds. So in this case, carbon one has very fewer bonds than the other and than the other carbons around. So what will happen is that there will be no longer a double bond because hydrogen will take over and will bond with the carbon. So this will become a normal cyclohexane. And as for the chlorine, it will bond with the second carbon. So the final I mean their fusion looks like this. So in the next problem that we will be tackling, that we're going to showcase the addition of waters to an alkyne. Okay, suppose that we have a CH3 bonded to a carbon, and then triple bond of C, and then here H, and then we're going to have an 2O with a catalyst of a 40%, ano. So let's have a let's pretend that this is a acid catalyst, and what will happen is that the reaction will have be like this: CH3 and C. So the first carbon, or this carbon in the CH2, there are two
hydrogens, right? I mean hydrogens, there are two hydrogens. So the first hydrogen will go here because this has a lesser bond. There is a lesser hydrogen present here more than the rest. And then the OH will be here. So that is the reaction between the H2O and this one, and this alkyne. Okay, next. So we have here the addition of H to the alkenes. So in applying this order, or in applying this order, we need to follow the mathematical rule, which is the rule states that with the symmetric alkenes, the carbon with more hydrogen group gets attached to the substituents. Alternative hydrogen atom is added number of hydrogen and the carbon to the least bond. Okay, suppose that we have a, uh, a bond here. So this is going to be alkene. We are asked to have an alkene. And then our HX will be HBr. Okay, so what happens is that the based on the mechanical rule that I have stated earlier, that the hydrogen hydrogen is um prone to attaching to the areas of the carbon that hasn't or has at least bonds. So in this scenario, or in this structure that we have, the one two the second bond has the least hydrogen or has the least bond. So our hydrogen has bonded in here, which is now here. So in terms of our bromine, it goes here. So our finished product is this. Okay, so next is that we have the addition of two hydrogens to an alkyne. Okay, so for example, we have an alkyne here, one alkyne. We have R, C, we have a triple bond here that signifies that this is a alkene, alkyne. Then going to have our two hydrogens here, and let's have a these. Okay, so this is a PDC. Then so our reaction will be this. Put my R here. So what happens that the two hydrogens bonded with these two carbons. So meaning that uh, they have two bonds now, which means that they no longer have a triple bond, and their triple bond becomes a double bond. And so if we to add another hydrogens, a pair of hydrogens, with also using a PDC, then the result will be like this. So that is an example of adding to an alkyne.
So in our number three, the question is, what are the steps in radical polymerization? Okay, so in the steps in the radical polymerization has three steps. The first one is initiation, the second one is propagation, and the last stage is the termination stage. Okay, so here are the processes. First, initiation of free radicals kickstart the polymerization process. After initiation, it attacks another monomer subunit. After propagation stage, termination is the final step. It occurs in different stages. If longer chains are expected, the initiator concentration should be less, otherwise many short chains will form.
Number 4 in lesson 8. Differentiate between monomers and polymers. So monomers from the Greek word mono meaning one. Mers means part. Monomers is a single atom or small molecule or molecular fragment. Polymers. It is a combination of single atom bonded with another atom to form a larger molecule known as polymers. So, number 5. Give at least two examples of conjugated dienes. So, conjugated. Conjugated is the double bond separated by single bond. Here is the example of conjugated dienes. 2 and 3 heptadiene because heptane because we have 7 continuous carbon. And the second example is 2 bromo 2 and 4 hexadiene because we have 6 continuous carbon hexane and we have 1 bromo in a second carbon, so 2 bromo and 2 and 4 hexadiene. That's all.
Okay, so in number six, what is the difference between oxidation reaction and reduction reaction? Okay, so oxidation occurs when a reactant loses electron during the reaction. It also refers to the gain of oxidation numbers. So basically, um, oxidation is the equivalent to um, reduction, even though it sounds like an addition, but in the reality and in the process between the oxidation process, it um, gets or it causes an electron to lose. While in the reduction, on the other hand, gain a hydrogen atom or electropositive atoms. So reduction is gain, and it's quite opposite of this is the name of the product. So reduction. So to summarize everything, reduction is the gain of hydrogen, and meanwhile oxidation is the loss of electron.
Okay, so for our item number 7, our task to give a one simple equation showing addition of x2 to an alkene. Okay, so for example, this, this. So there is a cyclo it has a bond. So if you are to add a Cl2 here, this will result into a this will result to this product. So of course, H3 will be in the upper one, and then Cl will be in here, and just like that.